Hi and welcome back. In the previous video lecture, we gave some MPC design guidelines for constrained linear systems. There we explained how we can compute the terminal cost function and the terminal set xf, and in particular xf was taken to be the maximal invariant set for a linear system of the form xt plus 1 is a bar times xt, subject to certain constraints. And we even gave an algorithm with which we can determine that set O infinity. The problem with this approach is that it can lead to a terminal set which is described by a very large number of constraints. So xf can be a very complicated object. In this video lecture, we will follow an alternative approach that leads to significantly simpler terminal sets. Perhaps smaller, they're not maximal anymore, but definitely sets with a simpler representation. These are the so-called ellipsoidal invariant sets. So an alternative choice for an invariant set is the collection of sets E with subscript alpha, which is the set of all x in Rn, such that x transpose px is smaller than equal alpha. This is nothing but a sub-level set of Vf. Now the task is to determine a positive alpha such that E alpha is a subset of x kappa f. If that's the case, then E alpha is an invariant set for xt plus 1 is equal to a bar xt, subject to the constraints xt is in x kappa f. So exactly what we're looking for an invariant set for this closed loop system, for the system xt plus 1 is equal to a bar xt. Only here it will not be maximal, but that's okay because we have a simple representation. Note that this matrix P is exactly the same matrix as the one we have used in VF. So this matrix P comes from the solution of DARE. Now let's see how we can determine alpha. And in fact, we're looking for the largest possible value of alpha, such that E alpha is a subset of x kappa f. Now x kappa f is it's a polyhedron. So it is a set that is described by a fixed number, a finite number of inequalities of the form hi transpose x less than or equal bi. Let's say we have s such inequalities. Then what does it mean for E alpha to be a subset of x kappa f? It means that hi transpose x is less than or equal bi for all x that are inside E alpha. So if x is in E alpha, then this same x must, of course, satisfy all inequalities that describe x kappa f. Now, if we follow exactly the same procedure as before when we talked about inclusions of polytopes, so we do exactly the same thing here, we will end up with this condition that the maximum of hi transpose x over all x's that satisfy the condition x transpose px less than or equal alpha, so that this whole thing, the maximum, is less than or equal bi for all I that are from 1 up to s. This must be familiar because it has the same form exactly as previously when we had talked about an inclusion of when we had discussed under what conditions one polytope is a subset of another polytope, or one polyhedron is a subset of another polyhedron. The good news here is that there is a closed form expression to compute this maximum. So previously, when it came to polytopes, that was a linear optimization problem, that was a linear program, and we said that we can solve it using software. But now the good news is that there is really a closed form expression to compute this maximum. And this closed form expression is given by this equation over here. So the maximum of hi transpose x over x transpose px is less than or equal alpha is given by the square root of alpha times the norm the Euclidean norm of p to the minus 1/2 times hi. Therefore, E alpha is a subset of x kappa f if and only if this condition holds for all I that goes from 1 to s. So if the square root of alpha times this norm that involves, you see it involves hi, must be less than or equal bi. Now if we solve for alpha, it is alpha what we're looking for. So if we solve for alpha, alpha must be no larger than this quotient bi squared over the norm of, you see, p to the minus 1/2 hi, the squared norm of that. And this must hold for all I. So for I equals 1, 2, 3 up to s. So alpha must be less than or equal all these quantities. So equivalently, alpha must be less than or equal the minimum of all these quantities. The minimum over I goes from 1 to s. The right hand side is the maximum value of alpha. It is the largest alpha we can choose is exactly this right hand side. So if we take alpha to be exactly equal to the minimum over I of bi squared over the squared Euclidean norm of p to the minus 1/2 hi, then we have that E alpha is a subset of x kappa f, and in fact it is the largest possible set of the form E alpha that can be inside x kappa f. If you take alpha to be larger than that, then E alpha will not be a subset of x kappa f. Now, by choosing ellipsoidal invariant sets, we avoid polytopic sets. We avoid polytopic invariant sets, which, as we said before, may come with a huge number of constraints, and they may overcomplicate the optimization problem. The optimization problem that we will end up with now will be a so-called quadratically constrained quadratic problem, QCQP, quadratically constrained quadratic problem, and there are lots of software that we can use to solve such problems. We may end up with a smaller terminal set. I mean, typically we do end up with a smaller terminal set because it's not the maximal invariant set anymore. It is the largest it's the largest ellipsoidal set, but it's not the largest set in general. We know that the largest set is polytopic. It has a different shape, a more complicated shape. And now this implies also that since we have a smaller terminal set, we also have a smaller domain of attraction and a smaller set of feasible states xn. But okay, swings and roundabouts, so we gain something, we gain in computational complexity, we have a more manageable problem, we lose in the size of xf and the size of xn. So thank you very much for watching, and until next time, goodbye.